Welcome to the world of control valves. Control valves are essential components in process control systems, responsible for regulating the flow of fluids such as gases, steam, water, or chemicals. A typical control valve assembly includes the valve body, internal trim parts, an actuator for movement, and various accessories like transducers and limit switches. Modern processing plants, control valves help maintain process variables, like pressure, flow level, and temperature, within desired ranges, ensuring product quality and operational safety. There are two main types of control valves: sliding stem, which use linear motion, and rotary, which use rotational motion. Understanding these basics set the stage for exploring their terminology, functions, and critical role in process industry. Let's dive into the terminology of sliding stem control valves. These valves use a stem that moves up and down to position the closure member, which regulates flow. Key terms include actuator stem force, which is the net force available for valve plug positioning, an angle valve where inlet and outlet ports are perpendicular. The bonnet houses the packing box and stem seal, providing access for assembly and actuator attachment. Other important parts are the actuator spring, which returns the stem to its original position, and the actuator stem, connecting actuator to valve stem. Understanding these terms helps in identifying valve components and their functions in process control. Bonnet is a crucial part of the valve, containing the packing box and stem seal, and often providing guidance for the valve stem. It can be bolted, threaded, welded, or integral with the valve body. The packing box assembly seals against leakage around the closure member stem and includes various components like packing rings, lantern rings, and anti-extrusion rings. Proper packing selection and installation are vital for leak-free operation and longevity. The bonnet also serves as the main opening for assembling internal parts and attaching the actuator, ensuring the valve operates reliably under varying process conditions. Closure members are the movable parts inside the valve that modulate flow. In sliding stem valves, this is often called the plug. The closure member guide ensures precise alignment during movement, which is essential for accurate flow control and minimizing wear. The cage, another key component, surrounds the closure member and can provide flow characterization, stability, and a seating surface. Proper guiding and cage design help maintain valve performance, reduce vibration, and extend service life. These features are especially important in applications with high pressure or temperature variations. Actuators are devices that provide the force needed to move the valve's closure member. There are several types. Diaphragm actuators use compressed air acting on a flexible diaphragm, while piston actuators use a rigid piston. Actuators can be direct acting, where the stem extends with increasing pressure, or reverse acting, where it retracts. The actuator's design, including springs and seals, affects the valve's responsiveness and reliability. Choosing the right actuator type is crucial for ensuring the valve operates correctly under different process conditions, especially in systems requiring precise control or rapid response. Effective sealing is vital for control valve performance. Packing materials such as PTFE or graphite are used to prevent leakage around the valve stem. The packing box assembly may include followers, lantern rings, and wiper rings to enhance sealing and reduce friction. Bellows seal bonnets offer an alternative for applications requiring zero emissions, using a flexible bellows to isolate the process fluid. Proper selection and maintenance of packing and seals ensure long-term reliability, minimize emissions, and comply with environmental regulations, making them a key consideration in valve design and operation. Rotary control valves use a rotating closure member, such as a ball, disc, or plug, to regulate flow. Key terms include full ball, which refers to complete sphere with a cylindrical flow passage, and segmented ball, which uses a partial sphere for specialized flow control. The actuator lever converts linear actuator motion into rotary force, positioning the disc or ball. Rotary valves are known for their streamlined flow paths and are often used in applications requiring high flow capacity or minimal pressure drop. Understanding these terms helps in selecting the right rotary valve for specific process needs. Butterfly and ball valves are common rotary valve types. Butterfly valves use a rotating disc to control flow and are valued for their compact design and low pressure drop. Ball valves, including full port and segmented designs, offer excellent shutoff and are suitable for high-capacity applications. The V-notch ball design provides equal percentage flow characteristics, making it ideal for precise control. Both types can be equipped with various actuators and are available in a range of materials to handle different process conditions, from corrosive chemicals to high-temperature steam. Control valves are defined by their functions and flow characteristics. Key concepts include fail-closed and fail-open positions, which determine the valve's response to loss of actuating energy. Flow characteristics describe how the valve's flow changes with travel. Linear, equal percentage, and quick opening are common types. Rangeability measures the ratio between maximum and minimum controllable flow, indicating the valve's flexibility. Understanding these characteristics is essential for selecting a valve that meets process requirements and ensures stable, efficient operation. Process control involves a variety of terms and concepts. The control loop is the foundation, consisting of sensors, transmitters, controllers, and final control elements like valves. Deadband refers to the range where input changes don't produce output changes, while dead time is the delay before the system responds. Gain describes the ratio of output change to input change, and loop gain combines the effects of all components in the loop. Familiarity with these terms is crucial for understanding how control valves interact with the broader process control system. Deadband is a significant factor in control valve performance. It refers to the range where changes in controller output don't result in movement of the valve, often caused by friction, backlash, or shaft windup. Excessive deadband can lead to poor process control, as small corrective actions are ignored until the signal exceeds the deadband threshold. This can cause oscillations and increased process variability. Minimizing deadband through good valve design and maintenance is essential for achieving tight control and reducing variability in process operations. Friction and backlash are primary causes of deadband in control valves. Friction arises from contact between moving parts such as seals and packing and can increase over time due to wear or loss of lubrication. Backlash, often found in gear drives or actuator linkages, results in lost motion when changing direction. Both issues reduce the valve's ability to respond to small control signals, leading to increased process variability. Regular maintenance and proper selection of valve components help mitigate these effects and ensure consistent performance. Design of actuators and positioners greatly influences valve performance. Positioners ensure precise valve movement by comparing the control signal to the valve position and making adjustments as needed. High-gain positioners can improve response time and reduce deadband, but must be matched with the actuator to avoid instability. Pneumatic relays and boosters are used to amplify signals and provide the necessary force for rapid valve movement. Selecting the right combination of actuator and positioner is key to achieving optimal control and minimizing process variability. Valve response time is critical for effective process control. It's measured by the T63 parameter, which includes both dead time, the initial delay, and dynamic time, the time to reach 63% of the final value. Fast response to small signal changes is essential for reducing process variability. Factors affecting response time include actuator size, positioner gain, and supply pressure. Properly designed valve assemblies can achieve rapid and consistent response, improving overall loop performance and product quality. Dead time is the interval between a control signal change and the first detectable valve movement. Dynamic time is the period required for the valve to reach a significant portion of its final position after movement begins. Both are influenced by actuator design, positioner gain, and supply pressure. Minimizing dead time is especially important in fast process loops, where delays can lead to instability or poor control. Consistent response in both directions is also crucial for effective loop tuning and process optimization. Instrument supply pressure directly impacts valve performance. Higher supply pressure can increase actuator force and speed, but may also raise air consumption and affect positioner gain. Fixed-gain positioners are optimized for specific supply pressures, and deviations can reduce performance. Efficient positioner designs balance high gain with low air consumption, ensuring rapid response without excessive energy use. Understanding the relationship between supply pressure and valve dynamics helps in selecting and tuning control valve assemblies for optimal operation. To achieve tight process control, it's essential to minimize valve assembly dead time. This involves reducing deadband from friction, shaft windup, and actuator or positioner design. Spring and diaphragm actuators generally offer lower friction and more consistent performance over time compared to piston actuators. High-gain positioners further enhance resolution and responsiveness. Selecting the right combination of valve, actuator, and positioner, along with regular maintenance, ensures minimal dead time and optimal process performance. Type and characterization of a valve significantly affect its control performance. Globe, butterfly, and ball valves each have unique flow characteristics: linear, equal percentage, or quick opening. The inherent flow characteristic describes how flow changes with valve travel at constant pressure drop, while the installed characteristic reflects real-world conditions. Selecting a valve with the right characteristic for the process ensures stable control and minimizes variability, especially when process conditions fluctuate. Stalled gain measures how much the flow changes for a given change in valve position under actual process conditions. Loop gain combines the effects of all components in the control loop, excluding the controller. Maintaining a consistent loop gain, ideally within a 4:1 ratio, ensures stable and optimal process performance. Excessive variation in gain can lead to instability or poor control. Proper valve sizing and selection are critical for keeping installed gain within acceptable limits across the operating range. Optimizing process control requires careful selection of valve style, size, and flow characteristic. The goal is to maintain a uniform installed gain and a linear installed flow characteristic across the operating range. Oversized valves can lead to excessive gain at low openings, causing instability and increased variability. Using valve trims or nonlinear characterization can help match the valve's response to process needs. Ultimately, process optimization depends on choosing the right valve for current conditions and being prepared to adjust as requirements change. Proper valve sizing is essential for process control. Oversized valves can cause high gain at low openings, leading to instability and poor control. Undersized valves may not provide sufficient flow. The sizing process considers factors like required flow rate, pressure drop, and process conditions. Using the correct equations and sizing coefficients ensures the valve operates within its optimal range, providing stable control and minimizing process variability. Refer to detailed sizing guidelines for specific applications. The economic benefits of selecting the right control valve are significant. Improved valve performance reduces process variability, leading to higher product quality, less waste, and increased throughput. Even small improvements in variability can translate into substantial cost savings over time. Investing in well-engineered valves may have a higher upfront cost, but the return on investment is quickly realized through better process efficiency, reduced energy consumption, and lower maintenance costs. Performance testing, such as the Signature Series, benchmarks valve assembly performance before shipment. Tests include configuration display, status monitoring, and dynamic error band curves. These benchmarks provide a reference for future comparisons, helping users track valve condition and performance over time. Regular diagnostic testing ensures valves continue to operate at peak efficiency, supporting predictive maintenance and minimizing unplanned downtime. Summary: control valves are critical to process optimization. Their selection, sizing, and maintenance directly impact process variability, product quality, and profitability. Dynamic performance characteristics, like deadband, response time, and installed gain, must be considered alongside traditional specifications. True process optimization requires a holistic approach, treating the entire control loop as an integrated system. Regular testing and benchmarking ensure valves continue to deliver optimal performance throughout their service life. Control valves come in various styles to meet different process needs. Globe valves are popular for their precise control and versatility, available in single-port, double-port, and three-way designs. Angle valves are used where space is limited, often serving as both a valve and an elbow. Sanitary valves cater to pharmaceutical and biotech industries, emphasizing cleanability and compliance with strict standards. Each style offers unique advantages, and selection depends on process requirements, fluid characteristics, and installation constraints. Single-port globe valves are the most common, offering simple construction and reliable shutoff. Cage-style valves use a cage to guide the plug, retain the seat ring, and provide flow characterization. Balanced designs use seals to minimize unbalanced forces, allowing for smaller actuators. Cage-style trims can be modified for noise attenuation, anti-cavitation, or severe service. These features make them suitable for a wide range of applications, from standard process control to challenging environments. Double-ported globe valves were historically used for viscous fluids or where contaminants were a concern. They offer balanced dynamic forces, allowing for smaller actuators, but are less common today. Three-way valves provide converging or diverging flow paths, useful for mixing or splitting streams. These valves are available in various materials and configurations to meet specific process needs, including high temperature or sanitary application. Proper actuator selection is crucial for reliable operation, especially with unbalanced plugs. Sanitary valves are designed for industries where cleanliness is paramount, such as pharmaceuticals and biotechnology. These valves feature smooth, polished surfaces, self-draining designs, and materials certified for human consumption. They support clean-in-place CIP and steam-in-place SIP processes, ensuring no bacterial growth or contamination. Elastomers and metals are selected for compliance with FDA and other standards. Sanitary valves are essential for maintaining product purity and meeting regulatory requirements. Butterfly valves are known for their compact design and low pressure loss. They are economical, especially in larger sizes, and are available with single or double offset designs. The disc rotates away from the seal after a certain angle, reducing wear and allowing for tight shutoff. Butterfly valves are suitable for applications requiring large flow capacity and minimal installation space. They can be used for throttling or on-off control, and are compatible with various actuator types. Segmented ball valves combine the benefits of ball and rotary valves. The V-notch segment provides an equal percentage flow characteristic, ideal for precise control. These valves are suitable for erosive or viscous fluids, slurries, and applications requiring high rangeability. The ball's shearing action minimizes clogging, and various seal materials are available for different process conditions. Segmented ball valves are widely used in industries like pulp and paper, chemicals, and wastewater treatment. High-performance butterfly valves offer effective throttling control and linear flow characteristics through 90 degrees of disc rotation. Double offset mounting reduces seal wear and friction, extending seat life. These valves are available in large sizes and can handle high temperatures and pressures. They are often used in general service applications where cost and size are important considerations. Bidirectional pressure-assisted seals provide tight shutoff, making them suitable for demanding environments. Eccentric plug valves are designed for erosive, coking, and hard-to-handle fluids. The eccentric disc minimizes contact with the seat ring during opening, reducing wear and improving throttling performance. These valves are constructed with rugged materials, including ceramics and carbides, for enhanced erosion resistance. They are used in industries like mining, refining, and power generation, where reliability and durability are critical. Eccentric plug valves offer both throttling and on-off control capabilities. Full-port ball valves are optimized for maximum flow with minimal restriction. They are ideal for applications requiring high flow rates such as bypass, batch, or emergency shutoff. Full-port designs allow for pigging and present little resistance when fully open. Attenuators can be added to control noise and vibration. These valves are fire-tested and certified for critical applications, offering reliable performance in demanding environments. Multi-port flow selector valves connect to multiple input lines, allowing for flexible flow routing and selection. These valves are used in applications where process streams need to be switched or blended without manual intervention. Their design ensures reliable sealing and minimal cross-contamination between streams. Multi-port selectors are valuable in complex process systems, enhancing operational flexibility and efficiency. Control valves are available with various end connections to suit different piping systems. Common types include screwed pipe threads, bolted gasketed flanges, and welded ends. The choice of end connection affects installation, maintenance, and leak tightness. Selecting the appropriate connection ensures compatibility with existing pipelines and supports safe, efficient operation. Understanding the pros and cons of each type helps in making informed decisions during valve selection. Valve bodies are constructed from a range of materials to handle different process conditions. Common materials include carbon steel, stainless steel, and exotic alloys for corrosion resistance. Material selection is based on factors like fluid type, temperature, pressure, and regulatory requirements. Using the right material ensures long service life, minimizes maintenance, and prevents failures due to corrosion or erosion. Always consult material compatibility charts when specifying valves for challenging environments. Selecting the right packing is crucial for leak-free valve operation. Options include PTFE veneering, laminated graphite, and specialized environmental packings. Each type offers different advantages in terms of temperature resistance, chemical compatibility, and emission control. Proper packing selection and installation reduce maintenance needs and ensure compliance with environmental standards. Regular inspection and replacement of packing materials are essential for reliable valve performance. Actuators come in various types to meet different control needs. Diaphragm actuators are common for precise, low-force applications, while piston actuators handle higher forces and faster response. Manual actuators are used for simple on-off control, and electric actuators provide remote operation and integration with digital systems. Rack and pinion designs offer compact solutions for rotary valves. Selecting the right actuator ensures the valve responds accurately and reliably to control signals. Valve accessories enhance functionality and performance. Positioners ensure accurate valve positioning, while IP transducers convert electrical signals to pneumatic. Volume boosters increase actuator speed, and safety instrumented systems (SIS) provide fail-safe operation. Other accessories include limit switches, solenoid valves, and handwheels for manual override. Choosing the right accessories tailors the valve assembly to specific process requirements, improving control and safety. Proper installation and maintenance are vital for valve longevity and performance. Key steps include reading the instruction manual, ensuring clean pipelines, and inspecting valves before installation. Good piping practices and proper flushing prevent contamination and damage. Maintenance strategies include reactive, preventive, and predictive approaches, supported by diagnostic tools. Using OEM parts and recommended spares ensures compatibility and reliability. Regular maintenance minimizes downtime and extends valve life. Control valves must comply with various industry standards and approvals. Organizations like API, ASME, ISA, and IEC set guidelines for design, materials, and performance. Product approvals for hazardous locations ensure safety in classified environments. Understanding classification systems, protection techniques, and enclosure ratings is essential for selecting valves that meet regulatory and safety requirements. Always verify compliance with relevant standards for your application. Isolation valves are used to stop flow for maintenance, safety, or process control. Common types include gate, globe, check, ball, butterfly, and plug valves. Each type offers different advantages in terms of shutoff capability, pressure rating, and ease of operation. Selecting the right isolation valve ensures safe and efficient process shutdowns, supports maintenance activities, and protects equipment from damage. Sustainability is increasingly important in valve selection and operation. Energy-efficient valves reduce consumption and emissions, supporting decarbonization and net zero goals. Greening initiatives focus on reducing environmental impact through material selection, design improvements, and collaborative ESG efforts. Companies are adopting sustainable practices to meet regulatory requirements and enhance corporate responsibility. Choosing valves with sustainability in mind contributes to long-term operational and environmental benefits. Safety instrumented systems (SIS) are critical for protecting personnel, equipment, and the environment. This includes layers of protection, safety integrity levels (SIL), and regular proof testing. Control valves play a key role as final elements in SIS, ensuring safe shutdown or process isolation during emergencies. Digital valve controllers enable partial stroke testing and online diagnostics, enhancing reliability and compliance with safety standards. Implementing SIS is essential for high-risk processes and regulatory compliance. Accurate engineering data is essential for valve selection, sizing, and operation. This includes material specifications, physical constants, and conversion tables for length, area, volume, mass, pressure, and temperature. Having reliable data ensures correct calculations and compatibility with process requirements. Reference tables and conversion formulas support engineers in designing and maintaining efficient, safe, and compliant process systems.